are all solid objects. Okay, so we try to represent all these solid objects as rigid body. Now, when it comes to flexible systems, we have a new concept, a new kind of robot called soft robotics, where we are not using motors and all that. Probably people try to use, air, the pneumatic devices in order to move the robot. So if you see a soft robots, we cannot represent that when you simulate in Matlab using a rigid body object. That is the main difference. So whenever you construct an object with a solid structure, we will use a rigid body. Whenever you go with a soft robot, a flexible system, where all our solid physics will not get applied, right? So for those objects, we will be using flexible systems. I hope I answered David. And then Vijay Lakshmi has asked how to download Matlab in PC. You will have to connect to MathWorks. If you have an educational or an institutional license, you can actually get from your respective institution, or otherwise try to go for a trial license. I guess a free trial license will be available for a period of 15 days. So probably you can even use the trial license to test it. So please go to MathWorks website in order to download it. Then what is joint access? I said, okay, I said you will have a joint which actually connects two links or two rigid bodies together. So when you're trying to actually connect two rigid bodies together, the joint is actually going to determine how the next rigid body is going to act or is going to move around. Okay, so the joint allows the next link in order to move in a particular axis. It can allow the movement in x-axis, it can allow movement in y-axis, or it could allow in z-axis. That is determined by the joint's axis. One good analogy that I would give you is, suppose you take multiple joints in your hand. Okay, you are trying to see how your hand actually works. Your shoulder has got a joint in your right hand. Okay, so your right shoulder has a joint. Now that joint actually connects two different bones. One is on your neck and the other one is the upper arm. Now you are able to move your upper arm in two different axes. One is x-axis you can move, and then you can also move it along y-axis, right? So the joint axis determines how the link attached to one particular joint can be moved. Is that clear, Nishita? Sorry, Nishita Agarwal. Okay. ROS package, you will, if you are trying to install ROS toolbox, okay, in Matlab, you will have to just download the toolbox, ROS toolbox, and install it. There shouldn't be any problem. But if you're trying to download some other ROS package, the actual ROS environment, you will have to install ROS into an Ubuntu system. You will not be able to do it on a Windows-based system. At least you need to have a dual OS. Okay, so if you are trying to get a Matlab toolbox, please check for ROS toolbox and then download it. Otherwise, you will require an Ubuntu system to install the entire ROS environment. Then the Matlab coding and output representation. Okay. Okay, so rotation actually depends on joint axis. So the axis, if you say the rotation is going to happen in x-axis, your joint axis will be represented as X alone. Whether it is going to be a clockwise rotation or anti-clockwise rotation will be represented in the homogeneous transformation matrix. I was talking about the homogeneous transformation matrix yesterday, where we were using cos theta and sin theta. In the 4-dimensional transformation matrix, the initial 3 columns was representing the rotation matrix. So there you will have to represent the difference between the clockwise and anti-clockwise representation. Balamurugan says there was an error. Can you just mention what the error was? Probably we'll discuss after this class. After this program. Just brief me about what error you got. Sometimes what happens is you would have already created a rigid body with a name body 1. Okay, so if you had already created a rigid body named body 1 and it is there available in your workspace, and then you're trying to again execute the same line in your program, in that case there will be a conflict saying that there is already a rigid body which is available with a particular name. Okay, so please clear all the variables and then try re-executing the program, because I don't see any error right now in the one single line of code that you have shared. So it should not be a problem, but please try again clearing the variables. So the only error that I could guess now is because you are executing the same line of code probably more than once. Crack version probably for Matlab is available, but when you try doing some research work, when you try to publish your results and all that, it is not advisable. So of course, I also have few students who have used crack version, but until you're trying to learn, it is fine. But then I strongly advise you to go with a licensed version. In transformation function, we have used some Cartesian coordinates, and those Cartesian coordinates are not the initial position. Those represents how much movement you are trying to do from the current position to the next position. Okay, so if you are moving your hand right now, wherever your hand is has a Cartesian coordinate, so that tells you the current position, and from that particular position you are trying to move, 2 meters towards the right, or 2 meters towards the left. So that 2 meters is what you are trying to represent in the transformation function. So it is how much you are trying to move. Okay, so I guess those who have not got the code for yesterday, probably today the organizers would send. I hope you all have received today's source code. So probably I'll start the presentation now if there are no more questions. Okay. Good that many of you have tried to understand the code. We have attempted it. Okay. Okay, so over to today's session, we have something called a differential drive robot. So today's exercise is going to focus more on this particular type of robot. Yesterday, what we did was, just an industrial kind of a robot. We called it even a SCARA robot or an articulated robot, where you are trying to link multiple rigid bodies with joints, and then the robot is fixed at a particular point. It is attached to a plane, and the links excuse me, the links actually move around the environment in order to do the action. Now today we are discussing about the next kind of robot, which is called a differential drive robot. Now what you see here as a differential drive robot is all these differential drive robots will be in action based upon two wheels. Okay, so sometimes you would also see robots like this, where you have two wheels at the back and then there is also a caster wheel at the front, something similar to our auto. Okay, so this is also a differential drive, but why we call these two? Now here you just have two wheels and here you have actually three wheels, but then these two robots are actually called differential drive robots because the entire functionality or the movement is based upon the motors that are connected to these two wheels. Okay, only depending upon these two wheels movement, the entire robot moves around the environment. So if you look at, I mean, this is a self-balancing robot. It can balance on its wheels. Whatever may be the weight, it can adjust itself. And at the same time, this is a very simple mobile robot. We have lots of students coming up with this kind of a mobile robot structure. So these two are differential drive robots. So now to start with, how and what is actually a differential robot and how do we work with it? Now, to understand this, to start with the kinematics of a differential drive robot. Now, the first thing that we need to know is there are two basic terms. One is L and then the other one is R. Now, L is actually the distance between these two wheels. Okay, so if I represent this robot with a diagram like this, now I would say the length between the right wheel and the left wheel is actually represented as L. And then the radius of the wheel, of course, both the wheels should have same radius. So the radius of a wheel is actually represented by R. Now these two are the measurements generally we will try to get from any differential drive robot, or if you are designing a robot, you should take into consideration these two because these two are going to play a major role. Now comes the next two terms, which is called VL and VR. Now what happens is there is a velocity at which the left wheel drives and there is a velocity at which the right wheel drives. Now what happens, I mean, because we will have two different motors. It is not one motor that controls both the left wheel and the right wheel. So here we have two motors. One motor drives the right wheel and the other drives the left wheel. So now what happens is if both the motors are running at the same speed, which means the velocity at the left wheel and right wheel are same. What happens now, if it is the same, then the robot actually moves in a straight line. Okay, so it moves along the straight line. Now these robots are going to work on the ground. It sticks onto a plane. It is not fixed, but then it keeps moving onto a planar structure, which is the ground. Right? So I don't have a z-axis here because these robots are not going to fly. They are going to move either in X or in Y. So we will have only two axes here. If both the velocities are the same, it is going to move along X. Now let us say if the left wheel is moving faster and right wheel is moving slower. Okay, assume the velocity here at the right wheel is 10 and left wheel is 20. Now what will happen? It will slowly start turning around. Okay, it slowly starts turning around. Now when the, I mean, this is like turning forward, and when on the other way around, when the right wheel is faster and the left wheel is slower, it is like turning the other way around. So whenever you try to turn, when the robot has to turn, the differential drive robot sees to it that it adjusts the velocity of a particular wheel in order to take a specific turn, right? Okay, now we will have to represent something more. What we told is, right now the robot, now whatever structure we have here, we are representing the robot in terms of a triangle now. Okay, just that, assume that, you know, I am trying to take one single point in this robot, assuming that this is the center. So I am just trying to take this particular point of the robot and then represent it in form of a graph, right? So x comma y is a point on the robot, and this robot is going to now have two more additional information. One is the linear velocity. Linear velocity is whatever speed or whatever velocity in which it is going straight, and at the same time there is also omega, which is actually an angular velocity. So there are two velocities that I have to consider when this particular robot moves, right? So there is a theta here, which actually represents how much is the angular tilt or angle, and what is the current pose of the robot to what axis is it actually facing towards. Now what happens, I am representing this, okay, if I know the linear velocity and if I know the angular velocity at which this particular robot moves, then I will be able to predict the new position of x and y, right? At present, x and y are here, but it keeps moving at a specific speed and it also takes an angular tilt. Okay, so after certain seconds, after say 5 seconds, where will this particular robot be? I should be able to calculate. How will I calculate? If I know the radius of the wheel, okay, and I know the distance between these two, so I will be able to predict the new x position and the new y position based on this particular formula. There is an entire derivation on this. In fact, mechanical students will know it, where, I mean, they would have learned it in the kinematics paper, I believe. Okay, so I'm not actually concentrating on the entire kinematics derivation in this class, but rather I am just taking up the final kinematics equation for one differential drive robot. Okay, so this is one way of representing or one way of predicting where my new x and y is going to be. And of course, the pose of the robot or the orientation of the robot also tilts, so that also can be identified, right? Now, we are identifying here the new value depending upon the radius, depending upon the velocity of the left and right wheel, and then depending upon the base length. Now, it is easy to know what is L and what is R, because when you design your robot, you will very well have R and L. But at each point of time, you will have to keep monitoring what is the velocity of the right wheel and what is the velocity of the left wheel at every moment of time. So that becomes a little complex, right? So what we do is, instead of going ahead with VR and VL, can I actually look at the linear velocity V and the angular velocity omega alone? Okay, so we will try to directly look at the model, taking into consideration only the linear velocities and angular velocities. Taking those parameters alone, I will be able to predict the same values of new x, new y, and the new phi value. So if provided this is my unicycle model, now remember, we will take both the equations, whatever we did using the individual velocities of the wheels and the unicycle model. Now what you understand here is, you will be able to predict mu x, I mean, which is x dash and y dash. Of course, the x dash and y dash can also be found using these equations. So which means this, I mean, r by 2 VR plus VL cos phi is actually equal to V cos phi. Right? So you can actually equate these two and you will be able to get a new equation here saying that, I mean, you're basically solving these equations. So once you solve, you will be able to get the velocity of the right wheel can be predicted using the linear velocity, angular velocity, and L and R. The same way left wheel's velocity can also be predicted. So what does this actually mean to us? Provided I design a robot by specifying the radius of the wheel and specifying the base length of the robot, okay, and then telling that at what velocity it has to move. And then if I also give the coordinates in the space, like from 0, 0, go to 10, 10. When I say that, your linear velocity, you mentioned the speed at which the robot can move. How do you represent that? It is based upon the motor that we select. Right? Each motor comes up with a specific speed limit. So you are going to set the speed limit. You will know at what linear velocity is it going to move. You will also know the angular velocity. So given all these conditions, I will be able to understand what is going to be my velocity, or what should be my velocity for the right wheel and what should be the velocity for my left wheel. Now, this is the only concept that we are going to see today, how one differential robot is going to do all these calculations automatically. You are not going to do all these calculations. Now, why I keep telling you all this is, it is easy for us to do it in Matlab because one single command does all the calculations and your robot starts moving. But as a student, we should understand what happens behind. Okay, what all calculations are happening behind in order to make it functional. Only then you will get a complete understanding of how a robot works. So I will directly take you now to the code. Okay. So what? Okay, so now what you see here, are you able to see my Matlab screen?
Yes, ma'am, it's visible.
Yeah, okay, good. So now what I'm trying to do is, now this piece of code is already available with you. So once I finish telling you what these actually is meant for, then you can start trying it out. Now what I have is, I'll do one thing. Okay, so now what I have here is, I have something called a path. Okay, I'm trying to create a matrix. Now what this matrix corresponds to is, I'm trying to have a representation of an entire floor. Okay, and on this particular floor, I am trying to mention the waypoints. Waypoints is, I'm trying to say the robot has to move through these particular points. Now, how will I represent points or the coordinates on a floor using an XY coordinate? So here I am trying to say 2, 1 is the first point from where the robot has to start from. So 2, 1, then it goes to 1.25 and 1.75, 5.25, 8.25. Now, these are the various points through which I want the robot to move through. Okay. Now, what I do here is, when you actually execute this, what you see here is, you find that there is a 6x2 matrix that gets created. Okay, when you execute this piece of code, you have 6x2 matrix that gets created. Those who have already worked with Matlab, this is quite fundamental. But for those who have not yet worked with Matlab, the way to create a matrix is just by giving a square parenthesis, and any space or a comma actually is a delimiter for columns. Okay, so 2, 1 will actually correspond to the first row and 2 columns, and then a semicolon is a delimiter for a row. So once semicolon is given, the first row is over, and then it starts with the second row. Right? Likewise, we have 6 rows and 2 columns representing 6 different points in my overall graph. Now I can even show you the graph here. Now you will get such a graph probably after a few more commands. So what you see here is the first point is 2 and 1. So 2 and 1, there is a point. And then 1.25, 1.75, there is a point. So what we are right now telling or creating a matrix is corresponding to the points that I am going to specify the robot as a waypoint. Okay, fine. Now, where do we use this? Now, we are using Ola. We are using Uber. We are using Google Maps and all that. And every time you want to find a route or decide to travel using these applications, supposing you give the goal, the destination and the source point alone, right? When you give these 2 locations, your application tries to find out an optimal route. Okay, so supposing from Gindi I want to travel till Egmore, then it tries to find the shortest distance between Gindi and Egmore. But at the same time, I am also saying that there are waypoints during this particular travel. From Gindi, I want to go to Adyar, and then from Adyar, I want to go to Mylapore, and then from Mylapore, I want to go to Triplicane, and then from Triplicane, I want to go to Egmore. Now, if I mention this waypoint, my route totally gets changed. Am I right? So these points are something like you mentioning that I need to go to Adyar, I need to go to Triplicane, and I need to. So you're mentioning that the robot has to travel through these particular waypoints. I hope I'm making it clear. Now, the initial location, the first location of the robot. Now, all these are just the variable names. So don't bother about what name to specify. You can use any name that is required. So we are just using that the initial location of the robot is going to be the first row of the path matrix. What is path matrix? We have created here. What is the first row? The 2 and 1 is going to be the first row. Why do I mention path 1, colon? Because I'm taking all the columns of path. Okay, I'll just show you an example here. Suppose I'm just creating a matrix P with 1 and 2, 3 and 4, 5 and 6. Okay, so what happens is I've just created 3 rows and 2 columns. Now, when I say I'm trying to take the first row, all columns, you will get 1, 2 alone. Suppose I say P of 2, colon, so you get the second row alone. So this actually takes the first row in the path as the starting location, right? And the last point, which is the goal point or the destination point, is going to be the last row. So when I say end, the end represents the last row. If I say colon, end, then what happens is taking all the all the rows and then the final column. Is that clear? So when I try to mention end, it corresponds to where you are representing it. This corresponds to row and this corresponds to column. Now I can, if I make it as colon, end, now what will happen is the goal will become the last column. Last column, you have 6 different values. That might not work actually, because you require only 2 values here. I am just trying to explain how this works. Okay, so end corresponds to last. Because it is available in row, it is taking the last row. Now I am trying to say the orientation of the robot right now. Now the orientation can be, it can face towards x-axis or it could face towards y-axis. So you're trying to say in which orientation my robot is currently present. So right now the orientation is towards 0. Now the current pose, whenever I represent the current posture of the robot, you will have to say X, Y, and the orientation, because Z is not there. I am not bothered about Z. All that I will require is where is it present at present, and then in which orientation it is present. Because if you look at the robot here, suppose this is the representation of the differential drive robot in Matlab. So what you see here is, if I represent the robot like this, my x comma y will represent the center point of the robot, and the orientation could be, it can face towards this side, it can face towards that side, it can face towards this side. So the orientation actually says how tilted the robot is, or to which axis the robot is actually facing. Okay, so now when I take the current pose, I am trying to take the initial location and the orientation. I am clubbing them together as one single matrix. Okay, so what did we have in robot initial location? We had as 2 and 1. Why? Because that is the first location that we have. So now the initial location is taken. The orientation, I said the orientation is going.
Ma'am, your voice has been muted, ma'am.
Yeah. Okay. Okay, so what we are trying to do is, we are trying to take the initial location here and the orientation, put together, it becomes my robot current pose. And once it becomes my robot current pose, I want it to be a columnar matrix. Okay, if you just combine these two, wait, just note this particular part. This is the output of this particular section. Okay, so now what you see is, you see that the robot current pose is actually 2, 1, 0, which is a row matrix. Okay, because already I had 2 and 1. So when you try actually combining these two as just a separator here with the space, it adds on one more column. For the later purposes, I would require the robot current pose to be represented as a columnar matrix. So just by adding a dash, I will make it a transpose of this particular the current matrix that I have. Okay, so now it becomes a columnar matrix because I've used a dash here. Now the next thing is what is more important. Now we have just defined so far what how to create the various properties of the robot, which is like, where is it going to be, how it is going to be, the posture, what are going to be the waypoints. So we have right now only set the environment, and we have told how and where it is going to move. Now comes the actual robot part. Now this command, the differential drive kinematics, this one single command will be able to create a robot. Okay, the differential drive robot for us. Now I'll just go back and then give you just a brief introduction about the differential drive model here. Now, this model actually has various properties. We are just trying to have a ready-made model that is available, which follows all the differential drive kinematics, whatever calculations that we discussed earlier. But it has actually 4 different properties. First property is the wheel radius. I hope you remember the terminology or the variable that we used in order to represent this from the diagram. Now, this wheel radius was represented by a capital R. Okay. Wheel speed range, we represented it as, the range of vehicle speeds. You're trying to represent the velocity. Okay. Then track width is actually L, the distance between the wheels on the axle, right? And then what vehicle inputs is going to get, which means you, from the model, when you are trying to represent a model in Matlab which corresponds to a differential drive model, what are the inputs that you are going to get from the vehicle? Are you going to get the input as the wheel speeds, which is the right wheel speed, and the left wheel speed, which is VR and VL? If you get the wheel speeds, then you will be going with the first model that we actually discussed. Okay, in order to predict your new X and new Y, you will be using the first model. If you're trying to use the vehicle speed heading rate, which is you are trying to see the linear velocity and the angular velocity, which is your omega and V. If you're using this, we will be using the later model. Okay, we had discussed 2 different models, how your differential drive robot will work. So if you use the first model, go with wheel speeds. If you use the second model, go with the vehicle speed heading rate. So these are the 4 different properties that we have. And wheel speed range is going to now represent, based upon the motor that we select, we will have the minimum speed and the maximum speed. Okay, so if you give a full power to the motor, then what will happen? It will go at the maximum speed. If you resist, if you are trying to, control using a PWM, you're using some mechanism in order to control the speed, then you will have some specific range at which you are trying to work with. So you can also mention the wheel speed range. I guess you are clear with all the 4 different properties. Okay, now do you want to try until here, just creating till the robots? Yeah, please try it out, and then let me know if you need any help. Try until creating the differential drive kinematics, this code, this piece of code. Okay, from path till here. Have you tried? Okay. Any difficulties so far? Okay, good. So then I'll just continue with the next. Now this is quite a simple piece of code. Now what you see here in the differential drive kinematics is we are representing the track width. I hope you remember we have 4 different properties for differential drive kinematics. Now here in this command, we are only representing 2 parameters, okay, or the 2 variables, and the remaining 2 variables we just leave it to be the default values. So we are mentioning that the track width is what? The distance between the 2 wheels that are available. So we represent it as there is 1 meter distance between 2 wheels. And what vehicle inputs we are trying to get? We are trying to get the vehicle speed heading rate. So which means I will be getting the linear velocity and omega from the differential drive kinematics. So when I execute this, now this is the property of the robot that gets created. Now what you see here is the vehicle inputs, whatever we have mentioned here has been assigned. Track width, because we have already assigned 1, it gets assigned. Now wheel radius and wheel speed range, we have not assigned any value. But what you see here is by default, it assumes it to be 0.05 and the wheel speed range is from -infinity to +infinity. So these 2 are the default values. Now if you want to set the values here, then you can actually add the values by representing the parameters here. Now I will just show you. If I say wheel radius, give the property name within quotation marks, I mean double quotes, and then you can actually say, suppose I'm using 0.6. Now what you see here is after executing this, you see that the wheel radius has changed to 0.6. So remember, these properties you can actually change depending upon what you are going to design, right? Fine. Now we'll just go ahead with the same piece of code, whatever we have. Now we are setting up the environment just to display how it is going to look like. So we are opening up a figure window. We are plotting. What are we plotting? From the first point in the path and to the second point. Okay, so you are trying to take the first column and the second column. So this is going to be your X and this is going to be your Y. And this is your description of what and how the plot is going to appear. K represents black color, and then double dash actually, K represents black color. The double dash actually represents that you're going with the dashed line, and then D actually represents the diamond which corresponds to each waypoint. Okay, so a combination of this is actually used in order to represent the plot. So the basic syntax for plot is actually X coordinate comma Y coordinate. So you're taking all the values in the first column for your X coordinate and all the values in your second column as your Y coordinate, and using this design in order to draw a plot. And we are also setting the limits for the plot by saying my x-axis is going to have a limit of 0 to 13 and y-axis also has a limit to 0 to 13. So now the figure window gets plotted with whatever description that we have. Now comes the controller. Now we will go back to the controller part. Is the PPT visible? Is the PowerPoint visible?
Yes, ma'am. Yes, ma'am.
Okay. Okay. So now when you use a controller, Now for this exercise, we are using a pursuit controller. We call it a pure pursuit controller, which is actually a geometric controller. Geometric controller means when you are giving a set of waypoints, and it uses the basic geometry in order to determine the path which is going to connect all these waypoints, right? So there is a control algorithm that is available which takes care of coming up with some geometry in order to decide what is going to be my distance, what is going to be the linear velocity and the angular velocity. So we are actually having all these properties for any controller which comes under a pure pursuit type. So I have waypoints. You know what waypoints are here. We have already declared a variable called path, which consists of the waypoints, the various points that we have. And then we have a maximum angular velocity. So we will say the maximum angular turn that you can take using this differential robot is this. So you can set a value for the maximum angular velocity. Look ahead distance is the controller has to understand how much I can look ahead, which is like you're basically having a sensor. The first diagram that I showed you for the differential robot had lots of ultrasonic sensors around, if you remember that picture, right? So each sensor will have certain amount of distance until which it can actually look ahead. So the maximum distance that it can sense using the controls is actually represented here, and the desired linear velocity, what is the maximum or the constant linear velocity at which the robot can actually move. So these are the various properties for any pure pursuit controller, and this is what we are going to use here. So what I do is I'm just calling for a controller pure pursuit and storing it as a controller here. I'm describing all the four properties that I just told you. So waypoints, we have already created a matrix called path, and then decide linear velocity, how much is the linear velocity that you want, angular velocity, how much you want, and look ahead distance, how much can I look ahead. So these are actually defined, and these values are user defined. You can define it. So after this class, probably you can even vary these values and see how it makes a difference in the robot's movement. Right. Now, I want to know the goal radius, which means this is my goal, right? So the robot keeps moving. When the robot keeps moving, if the goal radius that I'm going to set, suppose I set a huge goal radius saying that if it reaches this huge circle, then I understand that it has reached closer to the goal. That is enough. In that case, I will increase the goal radius. Okay, if I want to be more precise, and if I want the robot to move to the exact location that I want, then you will minimize the goal radius, right? So every time I try to find out the distance between the current position where my robot is and to the goal position. So what I do is I'm taking the initial location and I am taking the goal location. I keep subtracting the initial location from the goal location to understand the actual distance between the starting point and the end point. Now, why I use this norm is because this is actually a vector subtraction. So I'm trying to convert the value into, the subtraction into a vector again. So I'm just using a norm, basically like the typecasting, or the data conversion, the data type conversion. So I'm trying to subtract to find the distance between 2 points. Now comes the actual simulation. Now what I do here is the entire simulation or the entire kinematics, how frequently you want your controller to work, or how frequently the sampling has to be taken. Okay, so this is like you do a signal processing application, and then you keep getting signals, and then if you are trying to set a sampling frequency. What does that mean? When you get an entire signal, how many samples are at what frequency level you want to pick up one sample from the actual signal. So something like that. When I try to move, the controller has to take a decision on changing the velocity, changing the angular velocity or the linear velocity, or changing the speed. So whatever the controller has to decide, how frequently should it take a decision, and that is actually represented here by a sampling rate. So I'm saying that the sample time is 0.1, and the rate control is actually the sampling that we do. In fact, I should have a slide on rate control as well. Yeah, so this actually tells you how many times a loop has to be executed and at a particular frequency. So you are trying to execute something over and over again at a particular sampling rate. So we try to mention what is the desired rate, which is like, how many times it has to execute, or desired time period between execution. So you can actually mention at what rate it has to get repeated. So we are trying to say 1 by 0.1, which means that determines how many times the loop gets repeated here. And we also mentioned the frame size. A frame size here is going to say what is going to be my track width, which is like if this is my center point, the track has to be between these two. The track is what? The base, right? The robot's base should always be on the either sides of these 2 points. So how much is the track width which you are allowing to plot the transformation? Okay. Now, this is going to be the entire loop, which will be called over and over again until what? Until the robot reaches the goal position. So where are you going to start the robot from? You're going to start it from the starting position. This is what we have declared as a initial position. Now you see that the robot has moved so far. How did it actually move? Now, we are trying to use the controller that we have actually created here, because that is the one that is going to determine my angular velocity and the linear velocity, the waypoints through which I am going to travel. So take the current pose. What is the current pose? Right now, so far, the current pose is the initial position. Okay. Don't get confused with this, because the simulation has already got executed and it has already reached the goal position. But when you actually start, the robot current pose was here, the initial position and the initial orientation that we have given. So it will start taking up from the current pose and then try determining the V and omega. V and omega is what? The controller is going to give you an output of the linear velocity and the angular velocity. Now, the robot's velocity using the controller's input. Actually, the controller is going to give you the or is going to give you a suggestion to the robot saying that try using this linear velocity and the angular velocity. Now you are directly going to take these values and apply it on the robot. Okay, so you take these values and send it as an input to the robot. Now the robot is there, the current pose is there. From the current pose, it will try to use this linear velocity and the angular velocity, which means there will be a change with the robot's position and the orientation. That becomes your derivative. Derivative is actually the change that happens to the robot from the current position. So that gives you the velocity, the overall velocity. So now what happens? I'm trying to update the current pose. I'm trying to update the current pose with this velocity. So I determine the speed and then multiply with the sample time that I have. Okay, so that keeps updating the current pose. So the initial pose is now transformed and it has now become the new pose of the robot. Now, after one particular sampling time, I have got a new position at which the robot is. Now I will have to find out the distance from the current position to the goal position. So because I was here, probably the distance was different. Now I would have moved to some other point. Now the distance becomes different. Then I would have moved to some other point. Then the distance would become different. So every time for each sample I actually calculate, it keeps updating the distance based upon the current position. Now, all this is actually only for the display purposes. I am trying to use again the same K, D, the dashed lines and all that to represent. And this is just to represent the path at which the robot has actually traveled. So this is nothing to do with the robot's movement, but this is for showing you the animation in the screen. So I'll now run this section. Now what you see is from the starting position, it keeps moving. You see that there is a change in the angular velocity. Now there is a constant linear velocity, but it changes the angular velocity and then moves towards the goal position. Once it reaches the goal position, that's it. So this need not actually get executed over and over again, because the distance to the goal will become 0. Is that clear? So now I guess you also can try from the controller part till the end. You will be able to complete the exercise. Right now, please concentrate on just taking whatever code is given and try executing it. Probably after this training program, you can vary parameters and see how it changes in terms of the execution. Okay, so are you done? someone has got error in line 14. This line. What have you used? Differential drive kinematics. Just check if it is a double quote. The track width. It has to be a double quote. Okay, so if it is still a double quote, what is the error that you're getting? Okay, if it says undefined function or variable, in that case, you don't have the robotic system toolbox, I believe. Please check if the robotic system toolbox is available in Matlab, because these are inbuilt functions that are coming with the robotic system toolbox. If the toolbox is not installed, then these commands will not work. Okay, others, if you have completed, we can go ahead with the next exercise. Has anyone completed? How to see the graph or plot of robot. Now, what I have given here is actually a plot command. Okay, so this plot command will actually help you to identify where exactly the robot is. So we are only trying to use a plot command. Okay, so if you have completed, we'll go ahead with the next exercise.
Sure,
I
ma'am.
hope, yeah, okay. Okay, now with the second exercise, now what we have is, we are now going to actually introduce some maps. Okay, and now last exercise, what we did was, it was just an open environment where we gave some coordinates and we asked the robot to actually move around the given waypoints. Now what we are going to do is, we are trying to create a map, something like a closed room structure. Okay, now I've just used the example maps here in order to see how the robot moves around. You can also have your own maps actually created. Now I've also have another program just to tell you how a map can be created by your own. Okay, so what we have is, supposing I create a binary occupancy map and just create a section. Okay, so now what happens when I try to create a binary occupancy map of size 2,2, so you see that it actually creates a binary occupancy grid here with the same size that I have given. Suppose I try to create 10,10 and 20. Now what happens here is, it actually increases the size from 2,2 to 10,10, but there is also one more thing that is available here. This is not corresponding to your z-axis, it is corresponding to the resolution. Resolution is within one, in each number, within each number, how much resolution or how much sensitive areas that you can have. Okay, this is like we have a 15-inch screen and the resolution is 5 megapixels or 3 megapixels or whatever. So that determines the resolution, saying how many number of pixels are available within 1 square inch, right? So that actually, the same concept is actually represented here as well. So the first two values corresponds to the overall size, and the third value here corresponds to the resolution. So now you can actually create your own occupancy map by creating a matrix as well. Now what I've done here is, I've used an I command. I is actually a command, is a function that creates an identity matrix. Now what you see here is, I'm trying to create an identity matrix of size 100. So a 100 by 100 matrix gets created, and what you see is the identity matrix where the diagonal values are alone 1. So I use this I matrix, so which is assigned in P. So I use that representing my X and Y, and this actually represents my resolution. Okay, so I can create a binary occupancy matrix like this as well. Now, when I want to create an obstacle here, now what you see here is a line which represents the identity matrix, and then this is like an obstacle that is created in my map, like a wall that you saw in the screen like this, right? So we are trying to create an occupancy matrix using such commands, where I will try to take two functions here. One is a get occupancy and the other one is a set occupancy. Set occupancy is in order to say, at this particular location, given the coordinate of X and Y, and you're setting the occupancy value as 1, which means 1 dot gets placed in the X and Y coordinate that you have represented. And at the same time, if you want to know at one particular point whether there is an obstacle or not from the map, you will be using a get occupancy function. Okay, so these are the commands. If you want to create your own occupancy matrix, you will be able to do that. Now, right now for this example, what we are doing is, we are just using an existing map that very well represents a room kind of an environment, right? So I'm just converting it into a map, and that is shown here. Now, one factor that we need to remember is, when the wall thickness is this, and the robot that we had in the previous problem like this, okay, when the robot is like this, we are talking about only the center point of your robot as X, Y. Now, what will happen when the robot X, Y is actually taken here? Now, X, Y, if it can travel till this corner, what will happen to the remaining half of the robot from the center? It will actually crash on the wall. Okay, so you will have to actually inflate the map in such a way that you take the radius of the wheel or the base length of the robot into consideration and give enough space from the wall in order to avoid any crashing between the robot and the walls. Right? So now this process, we call it as inflating. So what we do is we take a copy of the map that is already available and we are actually inflating this map with the track width by 2. Why? Because the point that I have considered is actually at the center and the overall track width is from one wheel to the next wheel, but we will have to only increase half the size to avoid crashing onto the wall. So I am inflating with half the size of the robot. Now what happens to my robot, I mean what happens to my occupancy map becomes thicker. Okay, so if you see all these walls actually gets thicker just for the purpose that when the robot moves, half of the robot will not actually collide with the obstacles or the walls that we have. So I hope you understand the inflated map here. Now we have something called a PRM. PRM is actually a probabilistic robotic path planning method. So we actually are using a probabilistic method in order to go with the inflated map. So now the only difference that you would see here is just how you represent the binary occupancy map and then how you are inflating it, because the environment becomes totally different. And now what you see here is just that in the probabilistic method, you can set how many number of nodes and what is going to be the connection distance, which means what all connectivity can I have. Suppose I take a point from here, then the connectivity will actually be taking care of not colliding onto an obstacle. So without colliding onto the obstacle, how many connections can I make? That is what is actually identified. So if you see here, now from here, the code is going to be very similar to the previous exercise, because we have waypoints. The same waypoints are actually available here, whatever waypoints we were discussing earlier. Right, so the starting location and the ending locations are actually specified. Okay, between the starting and the ending location, it actually activates the controller takes care of the waypoint, and then you start from the initial location to the goal point. You're trying to find out the post distance goal and the entire while loop, which actually tries to determine the path between the starting point to the ending point is actually identified. So the end output will be something similar, but in the process, you are trying to consider what all probabilities are available. Now what you see here as a probabilistic roadmap that I told you as PRM. Okay, we are setting up a PRM here, right? So we are creating a PRM here, and then for the PRM we are saying how many number of nodes it can have and what is going to be the connection distance. So the distance between two nodes cannot be greater than 10. So all these are set up. So the probability will actually look at whether there is a possibility of getting this particular node. So that ends this particular exercise. Not much of a difference. But the application, if you look at, it is totally different. Okay, so in an open environment, if you are designing a robot where you don't have any obstacles, then you can go with the exercise number 1 that we have dealt with. If you have obstacles and if you want the robot in order to identify and find out its own waypoints without hitting on or colliding onto an obstacle, then you will have to go with different models are available, but here we are trying to actually go with a probabilistic model. Yeah. So I guess with that we come to an end to today's session. Now the session is open for questions.
So thanks a lot, ma'am. Now we
Yeah.
are starting the Q&A question. So you can ask your questions in the chat box.
Waypoint is one single point which is available which you are setting, saying that the robot has to move to this particular point. I hope there are no doubts, because I keep getting only the thank you link, thank you messages.
Guys, any queries you can ask in the chat box.
Path planning. Path planning is actually when you are trying to decide what path to take. In the current application, now see, we in this problem we have not defined the path matrix like what we defined in the previous exercise. In the previous exercise, what did we say? We told each and every waypoint. Okay, but here we are giving only the starting location and the ending location alone. So you are defining from where you are going to start and you're going to say where you are going to end. The algorithm or the